Yes, hello everyone. Welcome to my presentation. I hope you will enjoy it. As you can read in the title, I will tell you about the topic of fretting fatigue. And as you can see on this preview slide, we did some experiments on realistic components as well as on laboratory models. And then we developed a calculation method. Yes, and I will tell you about this in detail in the following. But at first, I will give you a short motivation. Fretting fatigue is a phenomenon that affects component connections, and it's due to very small slip amplitudes in the micrometer domain. And yes, a very good example is always this dovetail connection, as for example in turbo machines of airplanes. And there are many more connections that are affected. For example, these shaft hub connections, as you can see here, the press fit, like for example in wind energy systems, and also connecting rod connections, like for example in big ship combustion engines, as you can see here. But as I said, there are many more, and so we can say there are numerous frictional and form-fitted connections that are affected by fretting fatigue. Yes, and since this is the fact, we need any kind of failure hypothesis to assess all arbitrarily component, yes, which is affected to fretting fatigue. In my opinion, this must meet two demands, this hypothesis. The first one is that it has to determine the location of failure correctly. And the second one is that this failure hypothesis has to determine the degree of utilization or the fatigue correctly in quantity. Yes, and there are today many hypotheses for plane fatigue, and some of them are also often mentioned in connection with fretting fatigue. So first we could validate them, but therefore we need an object for validation. Therefore we did some experimental tests on these connecting rod connection, which I mentioned before, and we did some staircase tests in the high cycle fatigue domain. You see we have runouts with 10 million cycles, and furthermore you can see this connecting rods clearly failed due to fretting fatigue. You see the fretting scars, and this is due to elastic deformations in the parts here, and these elastic deformations caused these micro slips, and so the failure occurred. From these experimental experiments, we get information about the fatigue limit as well as about the failure location. And with these data, we now can do some finite element analysis and can validate our hypothesis on the contact surface. Yes, you see, for better visibility, I did this in a roll of view of this contact surface, and you see we have 6 hypotheses validated. These are the fretting fatigue damage parameter by Ruiz, the McDiarmid parameter, the parameter by Smith, Witz, Watson and Topper, the parameter by Fatemi and Saussure, a new one by Böhme, and the PIN by Papuga. You can see here as a reference, the dotted line is our experimental location of failure, and these white spots you can see here represent our maximum of the hypothesis, and you can see from failure location aspect these are very good, but if we now take a look at the degree of utilization, we see that it's far away from that what we want. We see the failure, the best hypothesis is here this PIN by Papuka with a failure of minus 52.6%, and the rest is more far away. The fretting fatigue damage parameter even doesn't allow to predict any degree of utilization. And furthermore, we see it's always in the negative domain. That means we are not even on the safe side. So we couldn't find any reliable hypothesis on these tested. Yes, and therefore we have to do something new or adapt something, but therefore we have to be clear about influencing factors. And since fretting fatigue is a combination of plane fatigue and fretting, we have influencing factors of both of them. And from plane fatigue we know this Hasse diagram, and it says that we have a plane fatigue limit and mean stress sensitivity as main influencing parameters. There are many more. And in fretting fatigue we have two main influencing parameters. These are the slip amplitude and the contact pressure. And these curve forms you see here, these are general valid for all materials. So that means for slip amplitude versus fretting fatigue strength we have this parabolic curve, and for fretting fatigue strength versus contact pressure these asymptotic curves, but we have to know the quantity, how it is. Yes, and this means we have our input parameters, which are fatigue loading, slip amplitude, and contact pressure. Then in our fretting contact, the crack initiation occurs, and at the output parameter, we get our fretting fatigue strength. And to separately analyze these influencing parameters, we have here this test bench. It's relatively unique. It consists of the following parts. We have on the upper and lower end an hydraulic clamp. Between that there's a tensile specimen. It's more like a classic pulsator. And then we have here this crosshead. It's mounted on these two actuator towers, and inside these towers there are piezoelectric actuators, which are the heart of this test bench. And if we look in detail, we see in this crosshead there are mounted flat pads, which serves as counterbodies. For better visualization, I have animated this test bench, and now here the part of the piezoelectric actuators you can see better. We have two control loops because these actuators can make a defined movement of our crosshead, and with it we can set a defined slip amplitude in this contact. It looks like this. It's upscaled because 10 micrometers you wouldn't see this good here. Yes, and then failure of our specimen occurs. Yes, and so we can do a separate analysis of slip amplitude, contact pressure, and our loading. And the results of this you can see here. We have fretting fatigue strength for different combinations of slip amplitude and contact pressure. And these green bars you see here, it's our plane fatigue strength for contact pressure of 0. And from this we can see that we have exactly this behavior I mentioned in the beginning for fretting fatigue strength versus contact pressure for constant slip amplitude. And from these three bars you can see the other behavior of fretting fatigue strength versus slip amplitude for constant contact pressure, this parabolic curve. And with this behavior, you see we have here some gaps in our parameter field. This is due to the limits of our piezo actuators. But from this behavior we know now we can extrapolate this fictitious interpolation points, and now we are able to do some curve fitting with this and determine an equation which is fretting fatigue strength as a function of slip amplitude and contact pressure. And with these data we are now going to adapt an existing failure hypothesis, we choose this of Böhme. This is has the following reasons. Papuga's benchmark showed that it's one of the best criteria at the moment. And furthermore, it is able to handle the compressive mean stresses which are occurring in the contact. Many others can't do that. And at last, the Böhme criterion was originally developed for a type of contact problem, even if it's not fretting fatigue. The original failure criterion is that we look how the equivalent stress of Böhme is compared with our plane fatigue limit in fully reversed axial loading, but this is a fixed value. And now we are going to replace this by our equation of fretting fatigue strength. And in the following, we can go back to our simulation of our connecting rod and get for every node the curves of slip, the contact pressure, and the stress components for every node over one cycle. Yes, for many different nodes. And from this, we now are able to define a slip amplitude, the mean value of the contact pressure, and with our stress, we can do our stress transformation for every cutting plane. Yes, and so we get at least this raw data, Böhme equivalent stress, slip amplitude, and mean contact pressure. As I said, over our developed equation, we can combine this to our fretting fatigue strength, and our degree of utilization is the Böhme equivalent stress versus our fretting fatigue strength. And now we see as reference here our experimental failure location. And this white spot here is our calculated maximum. And you see it's quite close. And if we now take a look at the failure of utilization rate at this maximum point, we are now at plus 25.68%. The error in the failure location is 0.3. Remember the other approaches, we see that we have now much better results, and we are even now on the conservative side. Yes, to summarize our work, what we did some experiments on connecting rod connections and validated then some failure hypotheses, but there was no satisfactory result. In the following, we did some experiments on double actuated fretting test bench, so we could do a separate analysis of the influencing parameters. We could derive an equation from that which describes the fretting fatigue strength as a function of slip amplitude and contact pressure. And then we did an adaptation of the hypothesis of Böhme according to this data, and the results showed much better quality. To get better than this, what we have, we focus in the future in the behavior of the mean stress sensitivity and the behavior of the coefficient of friction under these fretting fatigue conditions. Also, we have to validate other component geometries and investigate further material pairings, and yes, also the non-collinear fretting and fatigue is something we have to focus. Yes, thank you.